Folks, if we run out of chairs, there are several in the main area that you're welcome to bring in here too. 45% off. I'll email you. I'll email you the thing. You can have a seat up here if you want, but also I understand the compulsion to like. Sometimes I want to bring away too. Yeah, that's available. There should be chairs.
Good. How about you? No, I'll sit up there. I'll sit right up. I'll get the view. I just want to get to
Yeah.
I miss you already. Just a good thing there's not too much sun right now.
The sweets. Bring the sweets. Oh, IPA collection? Yeah, I got rodeo through that. There's a prop above you that you have to extract, but don't worry about it. It's on top. Yeah. You'll be good. You'll be good. I'll walk this way. Yeah, and everything will be fine. Yes, you just. Yeah, you just sign up. Hey, come back. Chris is coming from chaos and Odie. Yeah. Anywhere that's not here. It's just mysterious. Wait, Sarah, can you pass me that? Oh, yeah. Oh, this one? No. I fixed it. Whatever was proposed. I fixed it enough.
My president's wondered and it's scary enough.
We're meeting tomorrow, right? Do you have anything I need to look at before we meet?
Yeah, I'm going to start today in the afternoon.
Okay, great.
It's like a buzzball.
Terrorist defense in the morning. But I should have time early tomorrow morning to take a look at it.
I have a chair for you over here. I'm sitting too much. But it's like kind of, you have to do a quick Spartan race to the pier if you want it.
Where are they going to?
The other chairs are just the ones that are in the building. But I believe they exist. Like there are chairs upstairs, right? I could run up and get some. I'll get some. It's okay.
No,
Not other people. This is Hi, Meredith.
Hey, Chris.
How are you?
See you.
Good to see you too.
It's been a while. You're like all clean shaven.
What I do? Oh,
I feel like last time I saw you.
big beard. Relatively clean.
Yeah, it's been a few months, I think.
Do you have a small person?
I have a small person.
Yeah.
Did
That's
I
also
not tell
different
you
than
that?
last time. Probably you did.
Yeah, like 7 weeks out from small person. I know. Getting all these. Yeah, getting all these defenses out of the way
Okay.
for this one.
Understood. Whoa.
Yeah, like you guys all need to get out of here. So like, that might be me.
We should get matching common system centers.
Stickers on
Yeah. Like, we have real deadlines
Lucky
here.
enough to be in the presence of
Real deadlines.
We might be,
Not compromised.
some percentage of
That's
it.
good. I was hoping that would be for now.
Oh, yeah. I've been told that at MIT, the team shows up in skin suits. Oh, cool. Their team is much smaller, but
It's super arrow in case things go down and you need to get out of there quickly.
yeah.
It's a good chair. Chris Mack just got this.
So that's not happening.
We do not.
Something like that. What do I need to say? I want to go in.
Seriously. If you don't want to walk into it.
Hailstorm.
There's a time limit on this?
I was told like 55 minutes.
Okay.
With questions?
Let's go with 45.
We are.
Okay, that's good.
Should we
I'll
do
give you a,
that?
I'll give you a 5-minute warning about that.
Okay, sounds good.
Thank you all for coming. This is a cool moment for Ben, who I guess got here almost 6 years ago, is that right?
Yeah, something like that, maybe 7.
And Ben was a physics and statistics undergraduate student here. He has been a master's student in math and now in complex systems, which seems like a better fit, potentially, for what he's interested in after his successful 15 years on the pro cycling circuit is over. So anyway, we're really excited that you all came to see him, and Meredith Niles is the chair of the committee, is that right? Okay. Yeah. Meredith is a food systems professor in Rubenstein, Cal's, College of Arts and Life Sciences.
Agriculture and life
Agriculture.
sciences. Yep.
I don't know.
A little different.
I'm so sorry.
Yeah.
Yeah.
So tight. We actually do work together.
We do. Do you know what STEM stands for?
STEM?
STEMs.
Sense, yeah.
Stop right there. Yeah. Colleges are not such a big deal to us. It's like a weird thing. But, yeah.
Multidisciplinary now, it doesn't matter.
It's a very weird thing. Yeah. Okay. Anyway, Meredith's the food systems professor and has been working with Ben on some of this research, and we're really excited about it. So have I talked enough?
Yeah, I
Time
think
for you
that's
to
good.
go. Okay.
Yeah, thank you, Chris.
Go for it.
So yeah, as you said, my name is Ben. My full name is Benjamin Freixas Emery, but most people just call me Ben. And I've been told that the thesis is not being physically attacked in any way, which was kind of confusing to me and a little bit disappointing, just because I had already made arrangements to borrow this cycling team. So this will just be decoration, yeah, which is good because it's very fake. So what I hope to do instead is to just take you all on a road trip with me, a journey, a voyage, if you will, through the scientific discovery of things all just having to do with natural disasters and social media and communications, all of the above. So, because we're all in this together, I'm going to use the word we a lot, so don't let that freak you out too much. It's just because, this is just us, and I encourage you to ask clarifying questions throughout. Longer questions should wait till the end. But, and I encourage you to nourish yourself, and we'll be all just taking on this together, even though we have to share one sword between us all. So I'm going to begin with a roadmap, but we need a destination. So I'm just going to throw out some general questions that we're interested in. And the first is, so during a crisis, what does the online conversation between the individuals who are affected look like? I know that's very vague, but more specifically, who are the most reliable generators and propagators of information during these events? And so we'll explore these questions in a series of 3 stops. Stop 1 will be my contributions to a paper in PLOS called Social Media Usage Patterns During Natural Hazards, where we'll investigate audience size for the active Twitter users during these major events, and the relationship between the audience size and the change in their activity during an event, from before to during. Then we'll take a brief detour and just explore a simulation using models of the limitations of Twitter's data for network science. In particular, we like to use a sample. All of the Twitter data that we're working with, almost all of it, comes from a sample called the garden hose, which is a 10% sample of all tweets. And there are two major mechanisms that generate noise in this, and so we'll look at what that kind of does to our network picture. And then on the third stop, we'll take a deep dive into Hurricane Maria and look at the communication network of the victims of that particular disaster. We'll investigate it temporally as well as just the static aggregate, and we'll compare the word-level differences in conversations that happen in that network, both in time and just structurally throughout it. So, stop one. So again, we're interested in this concept of the people who are speaking, who are exchanging information during these major events, and so we need to select the users that we're interested in. First, we'll select the actual events, so we'll pick out the 5 most costly disasters between 2011 and 2016, adjusted for inflation. And those will be Hurricanes Irene and Sandy, 1 major flood in Louisiana, and then 2 separate outbreaks of tornadoes in the Midwest. And then for each of these, what we'll do is we'll take a 2-week period that's centered on the date of that particular event. And we'll identify all the users on Twitter who tweeted at least one of our hand-picked keywords. And these are all just keywords that either have to do with food security or disaster preparation or recovery, or even some words that specifically have to do with the event in particular, like you'll see Sandy and other event-specific words like that. So this gives us a group of users who we think are conveying important information during this. And so from here, we'll take these users and we'll look at the distribution of local network size. This is just kind of my fancy way of saying follower count. We're going to look at the number of followers that each of these users have. And so if you take out your binoculars, you'll see that these axes have labels. This image has gotten kind of destroyed by the projector, but it looks better on the screens. And so these are just follower count distributions. So on the x-axis, we'll have the number of followers, and on the y-axis, it's just the number of users who have that follower count. And this is log transformed on both the x and the y-axis. So if this were a linear transform, these distributions would just be, you would basically not even see them because they'd be hugging the far left side so tightly. So this lets us see them. And what we'll notice first of all is that they all have pretty heavy tails, which is good. This is consistent with just the normal behavior for online social networks in general. Also, there's some characteristic shelf behavior of the hurricane events, which we won't have time to explore in particular, but it's kind of an interesting situation. This shelf for the lower follower counts. But now what we really want is the relation between this and the way that these users behave. And so what we're going to do now is narrow our focus to Sandy because it has the most users, and this is just going to be kind of a complicated process, and we really only want to do it once right now. And so we'll go ahead and we'll take the users, our Sandy users, and we will compute a tweet rate for before and during the event. So our before period is just all of September, and then our during period will be October 21st through November 4th, all 2012 when it happened. And then for each of these time periods, we will take the earliest tweet that we find and the latest tweet that we find. And each of these tweets has a total tweet count field. So we know the total number of tweets for the user at these 2 times, and we can take the difference between them and divide by the time that's passed, and we'll get a tweet rate. And then after that, we will repeat this process. So this is a pair of tweet rates for before and during Sandy. And now we'll do this again for a collection of analogous periods of time throughout the year so that we have something to compare it to. So these are just separate pairs of times that don't coincide with any particular major disaster. And then what we'll see is, this is going to take some explaining. What we should just look at the left figure right now. What we have is on the x-axis is again the log transformed number of followers for each account, and then on the y is the log transformed fractional tweet rate change. So it's tweet rate during over tweet rate before. And so, and this is a scatter plot, kind of. If we just plotted all the points, each user would be a point on here, with an increase in a number of followers, but it would just be way too many points. So instead what we do is this heat map thing where the color of each square represents how many dots would be in that block. And then the color map is also on a log scale, so it's like a log, log, log plot. And then this ends up looking something like, so we have that for Sandy, and then we'll look at it again for the analogous pairs of times. So what we should be paying attention to is the difference between this and this. And what I would notice at first is that this seems to be a lot more symmetric along the 0 axis on the horizontal. Compared to this, which is kind of all more weighted towards the upper half, in particular in the lower area. Although you might not be too convinced of this yet, so what we'll do next is we'll break this up by order of magnitude. And so, breaking it up by order of magnitude, here we now have that, it's basically the same plot, except we've taken users with 1 to 10 followers, and then 10 to 100 followers, 100 to 1,000, so on, and made these little violin plots for the fractional tweet rate change for each of those followers in that category. And so these are basically just vertical histograms that have been reflected and painted green to look like the Grinch. And the black lines, these are actually 95% Bayesian confidence intervals for the means of those distributions. And what we notice here is that they're all pretty close to 0. They're almost all just a little bit above, but the ones that are the most notably above 0 seem to be these two right here, the 1 to 10 followers and 10 to 100 followers. And if you're not quite with me there, we can look at the actual numbers, because people like actual numbers, and we can see that, so this is the lower and upper bound for these confidence intervals, and the same for those. And the biggest differences in these intervals is for these two groups, the ones with the ones with 100 or fewer followers. So what does this mean? Well, we have this concept that comes from a psychologist, Dunbar, who has done work with primates, but perhaps the most famous result from his work is its implications for humans, which said that humans can only maintain meaningful relationships with somewhere between 100 to 250 people. This is often called Dunbar's number, although it's really kind of Dunbar's range of numbers. But for this particular finding, we had that the greater increase in activity came from people with 100 and fewer followers. And these are actually the people who could potentially have those close relationships with all of their followers, according to Dunbar. And then influentials, the big celebrities and people who have lots and lots of followers, they didn't change their behavior as much. And this is also consistent with a lot of findings in the literature regarding information cascades on networks, which put a lot of emphasis on the concept of hidden influentials, which are these kind of smaller nodes in networks which really propel these information cascades. So that's the first stop. Next, so for when we get to the third stop, we're going to be making a network out of Twitter data, and what I want to do first at this stop before that is take a look at some of the problems that might exist with painting that kind of picture with Twitter data. So first of all, the problems that we'll encounter. Twitter's garden hose, the sample that we use, contains only 10% of all tweets. So what does that do to our network? We're not really sure. And then a more interesting issue, and a more complicated one, is that Twitter leaves out important information regarding retweet chains. So what do I mean by that? I'll explain with a picture. let's say we have 3 users on Twitter, and I escaped the chains of physics years ago, but I still cannot resist the compulsion to call these people Alice, Bob, and Carmen. So Alice, Bob, and Carmen are on Twitter, and Carmen follows Bob, and Bob follows Alice, but Carmen does not follow Alice. Alice tweets something, and Bob sees it, Bob retweets it. That retweet constitutes this link from node Bob to node Alice. And then, because Bob has retweeted that tweet, Carmen sees it, and Carmen retweets that same tweet. And what we would want to see, because Carmen saw the tweet because of Bob, what we would want to see is that a link goes from Carmen to Bob. But Twitter doesn't record that. All that Twitter records is who is retweeting the tweet and who the original author of the tweet is. So what we see instead is something like this, where both of these links are actually going straight to Alice. And while Alice should have an in degree of 1, because there's one link pointing to Alice, and Bob should have an in degree of 1 for the same reason, we actually have that Alice has an in degree of 2, and these two both have in degree 0 in this little micro network here. And so this is going to make the network look a lot more star-shaped, and we'll investigate that. But first, we're going to need to synthesize a toy network that represents Twitter. So what we'll do is we'll initialize a Watts-Strogatz small world network. So this is n equals 100. There are 100 nodes in a ring. K equals 2. Each of those nodes is holding onto its 2 neighbors. And then P equals 0.05. We cycle through all of those links between the node neighbors, and with 5% probability, we break off that link and attach it somewhere else, anywhere else on that whole ring. And so that's what we start with. Then what we do is we randomly add links to this network. And the way we'll do that, we'll cycle through each possible pair of nodes 30 times, and then with probability that's proportional to the in degree that a receiving node already has, we will add a link from the first node to the second node that we've iterated through. So the probability that a node gets another link to it is higher if that node already has a lot of arrows pointing at it. So this is a concept commonly referred to as preferential attachment, or rich get richer, any of these things. And what we arrive at is the following Death Star. Here, the size of the node corresponds to its in degree, and the color of the node corresponds to its in degree, because I really like conveying redundant information with color maps. Speaking of which, this is the in degree distribution of this network. And so right now, we've got like kind of a mild heavy tail going on, but it's not like Dear Diary, today I found a power law or anything like that. But here's where we'll start with, and we'll say that this is something that Twitter looks like. Now let's sample the network. This will be analogous to if Twitter didn't do that rewiring stuff, but we still took the garden hose. And that, so again, we'll randomly select 90% of the links from our original network, and we get something that looks like this. And the in degree distribution, so this is the distribution of the number of arrows pointing at each node, doesn't really change too much compared to the whole network. So we don't see too much there, but now and we'll revisit this and measure it in a different way in a sec, but now we should look at the rewired network. So what we'll do here is we'll take our whole network and we'll iterate through all paths of 2 links. And with some probability, we will rewire them from paths to stars. They'll go from this to that. And the probability with which we do that will again be proportional to the in degree of the receiving node. And I told you the network was going to become more star-shaped. What I didn't say is that we're actually going to get the solar system. And this is kind of funny because, you know, lots of cultures worship the sun. In this case, this big node is like the big celebrity on our network, so there's like kind of a statement about celebrity worship or something, whatever. It doesn't really matter, stay woke. And here's the in degree distribution of this. So again, we ended up with way more zeros and one single hero that you cannot see at all. but way out there at 800. So, okay, now let's do things that good scientists do, and let's take a really complex phenomenon and break it down into one single number. And so we're going to take the sensitivity of centrality measurements. What do I mean by this? Each node can have its centrality measured in a lot of different ways, the same way that there are a lot of different ways to measure the size of an object or something. But either way, we'll pick some measurement and we will measure the centrality of all the nodes in the network. And then we'll define this sensitivity measurement. So this is the sensitivity measurement of centrality M of the transformation of a graph G to graph G prime. Graph is just a posh word for network. It means exactly the same thing. And it'll be this fraction here. NC is the number of node pairs whose rank order does not change from G to G prime. So it's like G prime, we rank all the nodes by their centrality, and then we do it again for the transformed graph, and then if we pick two nodes, and this one's bigger than this one, and then this one's bigger than this one again, same order, it goes into NC. Otherwise, it goes into ND. So what this really is the proportion of node pairs whose rank order doesn't change. So in this case, rho equals 1 means that the measure is very robust, and rho equals 0 means the measure is extremely sensitive. And here's what we end up with for the sampled network, the rewired network, and then the rewired then sampled network. And so what we have, first of all, and then these are 3 different ways of measuring degree. I won't have time to go into the specifics of how those are each calculated, but you can ask me about that later. And the first thing is that the degree is the most robust of any of them across the board, apart from this first column, which we'll just ignore. But the other thing is that the rewiring of the network actually has much less, or has less effect than the sampling. And sampling, or the rewiring of the network doesn't have, if we use either of these two measurements, either closeness or degree, the rewiring does not have much additional effect apart from just sampling. So this means that if we're using the garden hose, if this ordering is what we're concerned about, we don't have to worry as much about the rewiring that Twitter's doing. So just to reiterate, if your goal is just to pick out the most central nodes, you don't really care how you measure it, degree will be the most robust. Twitter's rewiring has a much bigger effect on the degree distribution. It did that huge first mover thing. Then the degree ordering, which we saw with the, the ordering was pretty robust, the rewiring. And then the 10% sample, again, adds not that much effect after the rewiring, unless we use betweenness, so maybe we shouldn't do that. We've made it to stop 3. So now, this is all about Hurricane Maria and the communication between victims of that, so we should just recap a little bit of what happened there. When Hurricane Maria made landfall, it was the first Category 4 cyclone to hit Puerto Rico in 85 years. And as it made landfall, it had sustained winds of 155 miles an hour, making it just barely not powerful enough to be classified as Category 5. Recovery from Hurricane Irma was still underway when this happened, and Puerto Rico's electrical grid was highly vulnerable, still is, and is partly due to the extreme debt that the island has accrued. And most of Puerto Rico lost power for anywhere between 2 months to 1 year. This makes it the longest blackout in U.S. history in cumulative customer hours, and the accepted death toll estimate is at just under 3,000. And the important thing to take into account there is that the vast majority of these deaths are attributed to the extended power loss, not the hurricane itself. So it's like if someone was diabetic and needed insulin, they might die because of that. If someone needed surgery, they could get an infection because the tools couldn't be properly sterilized. Lots of other reasons that extended power outages in a very hot climate can cause a lot of this. 89% of cell phone towers went down, not physically, but they became unuseful. But nonetheless, many Puerto Ricans communicated through hotspots of reception found along highways near San Juan. So if you're near San Juan and you went out onto the highway, you might find areas where there were just lots of people with their cell phones out connecting to their loved ones and the rest of the world in these handful of isolated spots. Okay, so what we want is to gather a collection of users on Twitter who we think may have been tweeting important information about the hurricane, about relief efforts, where to find supplies, all these things, during the preparation, the event, and the aftermath. To do this, we'll start with our box of geolocated tweets. Now, this is the one time where we actually have all the tweets. We have every single geolocated tweet. But geolocated tweets, because it's an option to turn that on, they comprise about 1% of all tweets that exist. So it won't be enough. But we'll pull all the users who we know tweeted from Puerto Rico on either of the days that the hurricane was physically hitting the island. And then from there, we'll go back into the garden hose and we'll pull all the users who @mention or retweet a geolocated user anytime between September 16th and October 15th. So a month is a good chunk of time to work with. Any more than that, and the computations start to get really heavy. And we'll start at September 16th, even though that doesn't quite center the event, because we're trying not to overlap too much with the aftermath of Hurricane Irma. Of course, that's basically impossible, but this is us kind of trying to do that. And then from that bigger group of users, we'll gather all tweets that come from those users that are in Spanish, because when Puerto Ricans communicate with one another, they're almost definitely speaking in Spanish. We'll filter on some keywords that are similar to the ones from the first stop, and we'll require a tag, because we're going to make a network out of this, and so we're going to need users to either retweet another user or @mention another user. And these are the words that we'll filter on. And again, it's very similar. It's words about food insecurity or supplies or words specific to the event, that kind of thing. There's some additional cleaning that I won't describe here because there's just no time, but you can ask me about that too, or read the paper. Okay, so now we're going to look at the network structure. And so this is the whole thing. The entire time period that I described, we're going to plot that all as this network picture. And we have this. So now, again, the size of a node corresponds to its in degree. The color actually indicates the communities as detected by a community detection algorithm. And so nodes that are the same color tended to talk to each other more than nodes of different colors. And the biggest nodes in this network by in degree tend to be, so far we notice, some local politicians. We have the governor of Puerto Rico, and then also a lot of local news outlets, some journalists, some meteorologists. That kind of thing is what we see the most. And then we also, in a separate community, we have some major musicians who are Puerto Rican. We have Shannon, Ricky Martin, Luis Fonsi are all in here. But they're in a separate community, which is interesting. Now we can look at the before network. So this is from the period of time before the hurricane actually hit. And there are way fewer nodes, first of all, because it's just a smaller period of time. Perhaps there was less activity, but we don't really know that. And the biggest nodes here are, again, we have a meteorologist and a weather station. So it looks like people were really paying attention to weather before the hurricane actually hit. It's probably a good thing to do. Now, after we start to see the structure that we see in the aggregate network, where we have this big conversation between the news outlets and the politicians, and we start to see the community of musicians pop out of here as well. So that's for after. What we're going to do now is we're going to start to look at the actual conversations that these people are having. So we have that these people are tweeting at each other, but what are they saying? To get at that, I'm going to have to introduce some friends to us that will help us figure this out. And our first friend is Shannon's entropy. So let's say we have a group of tweets that we strip away to just the words, and then we put all the words. We'll include hashtags and emojis, but we'll put them all into a bag, and we'll call that bag big P. And then little pi, that will be the probability. If you reach into that bag, you get the ith word. So the ith word might be huracan or like any individual word. So it's just the probability. This will just be the probability that you see that word. And this is a measurement of diversity of our text. So it becomes, it's its highest when all the words occur with equal probability, and it gets lower as the distribution becomes more skewed to fewer words. You can think of it as kind of the surprise of the words on average, so how surprising the words in P are on average. This is useful because it gives us some measurement of diversity of our text, but we want to compare conversations. So we'll need some more. And so here's callback Leibler Divergence. It's very similar to Shannon entropy, but now we have two bags of words. We have bag of words P and bag of words Q. And this is like how surprising the words in P are if we're expecting something that looks like Q. So this is pretty useful if we're going to compare conversations, but it won't quite do the trick because every word in P has to also occur in Q. Otherwise, this measurement will be undefined. So if we're comparing two separate conversations, this won't do. But we can modify it so that it works. And we'll just introduce one more, and this is Jensen-Shannon divergence. Now this is kind of a, we still have bag of words P and bag of words Q, but now there's a third bag of words M, which is just, you take Q, you dump it into the bag of words P. And that will be the combined bag of words. And so this, and then this is a weighted average of their callback Leibler divergences from the combined distribution. So this is like how surprising the words in P and Q are. Sorry, this is really low on the screen. You can also use those. If we're expecting their average. One more super useful property of this tool here is that we can do some algebraic acrobatics and like dance to the logarithm and blues and get this out of it. And now this is just one summation over all the words. And so we can look at the contribution of individual words by just ignoring the summation and just computing this for one single word. That's exactly what we're going to do next. We're going to look at the individual word contributions. And we're going to do that using a diagram called the word shift. So let's compare the conversation before the hurricane to the conversation after. So this will be really confusing at first. Each of these bars is the contribution of a single word to the divergence between our two conversations. And so the length of it is that contribution, and the direction that it's going corresponds to which conversation it was used more in. So vientos, or wind, that is used more before the hurricane. And then the color of each bar, that corresponds to the Shannon entropy of the conversation of tweets that use that word. And the reason I include that here is because it tells us that if a bar is darker, that means that word is used in the context of a more diverse group of conversations. And if a bar is really close to just completely white, that means that it was most likely used in just retweets of the same tweet. So that's useful for the context. And in terms of before and after Hurricane Maria, we see that we have words about the weather and the incoming storm and its properties being talked about, which makes sense. We have wind, sustained, category, these kinds of things. And then after, we have water. A lot of people didn't have running water. And then trash. There was trash everywhere. And one thing to note is that this is not impervious to other conversations that are unrelated kind of seeping in. So, for example, this hashtag here had nothing to do with Puerto Rico. And so that's just something that we kind of have to acknowledge and move on from. And so now we'll take a look at the between community version of this. So we're going to take the big community that contained the governor and all those news outlets and compare it to the community of those famous musicians. And it's kind of hard to see, but we have Maria on the left, so being used more by that conversation with the governor and the other people. And luz, this directly translates to light, but it really is used as a synonym for power in our case. So we'd be like, ya tengo luz, I have power, and so that's the context that that's using here. And then we have words about Puerto Rico that are used more by this community of celebrities and people talking to celebrities, but it also has words about Mexico and just other issues. It kind of seems less focused on Puerto Rico and more about just a general mix of Latin American issues. The same happens to be true with another major community in the network, where we have conversation about corruption in Latin America and that kind of thing. So what we get from this is that comparatively large communities to this biggest one seem less focused on Puerto Rico specifically. So the last thing that we're going to do is we're going to look at the evolution of this network in time, but we're going to focus on the top 50 nodes in the aggregate network. So what we'll do is we'll take those top 50 nodes and we'll look at them and say, what is this? So this is a politician, this is a journalist, and so on. And then we'll look at the in-degree of those, the combined in-degree of those categories over time. So this figure is going to be a lot to look at first. But what this is we have all the types, so like politician, citizen, musician, entertainer, weather station, so on. And then the height of each of these bars just corresponds to that combined in-degree. And so let's take a look at just politicians first. So we're looking at this blue at the bottom, and we'll see that they're a pretty consistent player, apart from there's some disappearances, but relatively consistent, but not overwhelming overall. Next, news outlets. These are by far the most consistently large presence in the network. Again, it does oscillate a little bit, but they are really there, and there doesn't seem to be any sort of major trend over time going on here. Journalists, similar, but there's less of that. These could have been combined with news outlets, perhaps. And then weather stations, we see there's one day where the weather stations come in the beginning of August, and they're very popular, or very prominent in the network, but it's mostly just leading up to the hurricane and during the hurricane, which, again, kind of makes sense. That's when people would be retweeting information that comes from weather stations. Government organizations, so this is where FEMA would be, or other like possibly nonprofit organizations or non-governmental organizations. But there are surprisingly few of these. At least it was surprising to me. It seems like FEMA wasn't really being utilized, or maybe they weren't providing that much information over social media that people were actually using, it seems like. And next, I just want to talk about the musicians and entertainers. So this is your Luis Fonsi and so on. Not much going on until October, and then there's this big spike, but again, they're kind of mostly talking amongst themselves and their fans. Doesn't seem like they're actually that connected to people on the island physically. And then an interesting thing is that this kind of resurgence over here is entirely accounted for by one single person. And there's a figure where this is broken up by individual user, where you can see that in the appendix. But this is all a Puerto Rican rapper called Residente, who was different from the rest of the musicians because he actually was speaking in that community with the governor and with those news outlets, arguing with the governor a lot. But he was on the island at this time, doing humanitarian work on the island. So that was interesting to see there. So what's going on here? Big picture. We have to remember back from the first stop that these hidden influentials, these people with these small followings, were playing an important role in information cascades. But what we kind of wanted to know from there was, where does that information originate? And so we will suggest that the information comes mostly from folks with these localized audiences, your local politicians, your local news outlets, that kind of thing. And not national celebrities or big agencies. So if we juxtapose this with Chapter 1, what we've basically done is we've been putting together these puzzle pieces where we don't know what the picture is supposed to look like at the end, but we've gotten enough pieces in these two general areas to start to see the big picture, where we've got information being generated by these types of people and propagated by these sorts of people, and then we just need those last couple pieces to link those clusters together and see what's truly going on. Okay, so this is the part of the musical where the whole cast and crew comes out and like does a dance or something. I want to thank my advisors, Peter and Chris and Meredith, who have been wonderful in helping me and guiding me through all of this. Also, Greg Warrington is a very talented mathematician and juggler, and he graciously started juggling this when I asked him to, which was wonderful. Also, Sam Rosenblatt, who's in the room, and Sarah Sugars, who is a student at Northeastern, basically peer ushered me into the wonderful world of network science. And Brooke Foucault-Wells helped me create the methodology for chapters 2 and 3, which was super, super useful, and I don't know what I would have done without that help. And this all happened at the Complex Networks Winter Workshop, which was organized by Juniper Lovato and LHD and Antoine Allard. Best conference that has ever existed. You should do anything you can to go to it. And also the pizza people. Thank you very much. Please memorize these references. I'm just kidding, I'll take questions now. Dave.
Ben, really great work. Chapter 2, you defined a measurement to compare two graphs, to compare to whatever centrality measures you want, and you go. So that was really interesting to me. So I was just curious.
Also, that's not my measurement.
Great, very nice. Well, whoever's measurement it was, it's an interesting measurement.
Yeah.
So what you're doing is you're comparing these order statistics. You're saying, okay, well, we're going to fluctuate around, and if you fluctuate, you get a +1, and that's it.
Yeah.
Did you ever investigate? So I don't know that this is the case at all. One can imagine, for example, I will take this listing of things that is sorted, and I will flip every, say, 10th pair, and you could have a very, very high. You flip every third pair. Okay. So you flip every third pair. You have every third adjacent pair. You'd have, I guess it's a low number. You would be you would have a big change. It's very sensitive. However, that might not, depending on what statistics you're doing after that, that really may not affect things all that much. If you change from having an in degree of 7 trillion, or 7,000 or something, to an in degree of 6,998, that's not really that big of a deal. Did you ever just look into something like that? I just wonder because degree centrality is great for some things and not really so great for others. Even though it happened to be the most robust thing there, that's a conclusion I might question in certain contexts.
Yeah, so it's really just, you're right, it's really just robust with respect to this particular measurement, which
Okay.
does not put any weight into how far away
Uh-huh.
two nodes
Uh-huh.
were in centrality
Okay.
in the first place.
Mhm.
So no, I haven't investigated that
Sure.
at all, but I
Yeah.
do expect it's very possible that those would be totally different. And we already saw that, we saw that the rewiring made this huge difference in the degree
Right.
distribution,
Right.
but then didn't really affect the degree
It
ordering
didn't,
that much.
and it didn't, once you subsampled, it didn't, yeah.
Right,
Yeah, that's interesting, okay.
Yeah, so that's definitely an important thing to note and an important thing for me to consider
Sure.
looking into.
I can ask more questions.
You could, yeah.
Yeah, we got more questions. Go ahead. Yeah.
I think Jane was first.
Well, this is not a scientific one, but
Oh,
you
that's
had
good.
mentioned in a previous presentation about your reasons for choosing which subject matter.
Uh-huh.
I was wondering if maybe you wanted to talk about that.
Oh yeah. So this is a very packed presentation, so it's kind of a lot of it was content, but I am very personally motivated to look into this particular thing because I have family members who were on the island during the hurricane, and so that actually happened just before Chris reached out to the lab and asked if anybody wanted to start working on natural disasters and communication surrounding that, and I was like, yes, I do, because this is actually has suddenly become very close to me, and it's really been it's been really interesting because that when the hurricane hit, we lost complete communication with our family members for a handful of days, and it was really scary, and it was just very eye-opening to see how long the struggle had to continue after that. It seemed totally unnecessary, and so I wanted to look into this and just see if there's anything that I can do that will eventually affect how people approach these issues, and I would like to, because it seems like it's just not being done as well as it possibly could. Balloon.
With work, I loved it.
Thank you.
And it's not really a question, but I really like how it's just 1 day of difference between the Mexican earthquake
Right,
and this, and like to see that how different are the response of each one of those. It's amazing. Even when you get these Mexican hashtags, it's very different from
Right.
what we could see.
Yeah, and I would like to do this just with a similar method, focus on the Mexican earthquake and maybe see how that's different, because really the Mexican hashtags that popped into our analysis, those were the one that happened by accident, and so it's not quite the most appropriate sample, but we still do see some interesting differences, and so I'd like to just see how that actually was different, because we have found actually part of that for that PLOS paper was in part of that PLOS paper we found some pretty major differences between disaster types and how the response looked in terms of the temporal distribution of the words being used, where hurricanes were kind of one shape, and again there were only 5 disasters, but it looked pretty different when you didn't have any known anticipation time, which is what an earthquake is. And so it would be interesting to see how that affects this sort of analysis. Sammy?
Hey Ben, great job, dude.
Thank you.
Forgive my base level of understanding
No,
of the data,
that's-
but was the lack of electricity accounted for in the tweets after Hurricane Maria happened?
Right, so that's actually totally a limitation that's worth acknowledging, because we have, so a lot of people went way out of their way to find these spots where they could talk to people, but really most Puerto Ricans throughout the whole span of this time did not have power, and so they were using, those who had generators could use those, and there were public generators, or public spaces with generators, kind of, except they were really mostly hospitals, which had to be dedicated to the people who needed them. So the sample is definitely greatly affected by that, because if someone's phone died, for example, then even if they got to this hotspot, they wouldn't be able to. I suppose they could actually charge their phone with the car that they used to get there, but it's definitely like that plays a major role, and it would be interesting to see what this would look like in a situation where power wasn't knocked out as badly as it was. Look,
Do you feel like your care has influenced your own use and presence on Twitter?
Yes. Kind of. I mean, I would imagine so. I wouldn't be able to say exactly how. But it's kind of a thing that happens with all of us who work with Twitter data, is that most of us really benefit from the intimate understanding of how Twitter works that you get when you're actually present on it. But yeah, this work in particular, it has attracted attention from other, I guess, communications scholars and people who work in disaster relief, and so that has kind of made me, I guess, more connected. But I'm sure most of the change I don't actually know, but I'm sure it exists. Yes. Sorry. What's your name again?
Ethan.
Ethan. Yes. Ethan.
Yeah. So I was wondering if you were to sit down with the powers that be, the supreme leader of disaster response, whoever that may be, what would you want them to take away from this presentation? What kinds of things do you see this research being used for?
So it's important to acknowledge that there are a lot of limitations, first of all, before I go saying, like, this is exactly what you should do. But what I would say is it looks like the information that you want to reach as many people as possible would spread optimally if you focus on just kind of average individuals, mostly people with these Dunbar-sized followings, and then also these kind of slightly larger users, or users with slightly larger base, but whose base of followers is localized on the area that was affected, which is kind of what we saw in the third chapter, where it seemed like the most prominent nodes were these public figure types, but whose audience would have mostly been Puerto Rico. Yes.
Ben, can this same technique be used to find non-person tweeters in a political type of climate? In other words, bots?
Bots are notoriously difficult to detect. There are certain ways that I think that this could be used, although I haven't tried. For example, when I showed the picture of the network with all the little circles, the size of those circles was determined by the number of arrows pointing at the circle. But what could do instead is make that correspond to the number of arrows pointing away, which is just the number of times that a user tagged someone else. And one type of behavior with bots, at least with bots that aren't very cleverly programmed, would be that they don't get much attention given to them, but they mention a lot of other users and they tweet a lot, and it's not very reciprocated. So I would say users that are overwhelmingly large in that type of picture I would suspect might be bots. That's really all that I can think of right now, but it's definitely an interesting problem to deal with, because bots are actually very difficult to detect, but sometimes that's really important to know. Ellen?
Yeah, again. I was just wondering if you have any information about Twitter penetration in Puerto Rico? Twitter penetration in Puerto Rico? Yeah.
entirely sure what you mean by
How many
that.
people use it?
Oh, okay.
How many and
Yeah,
the
so,
places?
yeah, I don't, one thing that I could do to try to figure that out is look at where specifically on the island those geolocated accounts were tweeting from. I'm guessing that it's mostly big, or mostly San Juan, I suppose. But yeah, I don't know for sure exactly how many Puerto Ricans use Twitter. And for this, it wasn't entirely necessary for them all to be Puerto Ricans. They could be people, you know, like me who have family members there and might use it to communicate with them, or might use it to, receive information in that kind of situation. But yeah, so I mean, the quick answer is no, but it's the kind of thing that would be important to know for sure.
All right, well, let's thank Ben again. So he's going to stick around and talk to his committee. Thank you for coming.
Take more food as you leave. Yeah, I'll see you soon.
Yeah, well, the chapter 2 was